Alright, good morning everyone. Let's start the class. Hope you have had a great spring break. And let's continue our discussion on clustering analysis. So we're going to quickly wrap up this topic and then we're going to start the next topic. So if you recall, we start to talk about this, we enter this new module, right, the second half of the semester. So we're going to introduce a bunch of machine learning algorithms. Right? So now we are moving away from the model-based learning and non-metric models. So we're going to introduce a bunch of machine learning models. But as we said, we start with this so-called unsupervised learning. All right. So this topic and then the next topic, those are the examples of unsupervised learning. So again, you know what is unsupervised learning? What is supervised learning? Unsupervised learning is where you do not have a clearly defined outcome variable or y variable to predict, to explain, right? Instead, what you want to study is the structure within, say, your x variables, right? So all the variables for unsupervised learning, you still deal with the usual data, you still deal with a lot of variables, and with a lot of observations. But those variables, all the variables that you utilize in unsupervised learning, you can view them as all x variables, all independent variables. I know clearly defined y variable, outcome variable information. So as we are doing here with cluster analysis and also with the next topic, cluster arithmetic. Right, so that's what we talk about. Then cluster analysis, the goal of cluster analysis is to what? You have a lot of observations. You want to group them into a few groups, a few clusters, a few segments. All right, and then we talk about a lot of the applications for cluster analysis. Right? Basically segmentation, right? Market segmentation is a leading example. You can also view cluster analysis as a method of so-called dimension reduction. Right? Think about that. You have thousands, you have millions of observations of records, but then you want to reduce the dimension. You want to perform some sort of customized design, certain the personalized strategy, but you do not want to personalize. You don't want to customize. Millions of different strategies, right? Instead, you may want to come up with a few strategies to be applied to, different techniques. Then how can you reduce that dimensionality from, say, millions of records to only a few groups? And cluster analysis can help you solve that. All right? So cluster analysis basically is just a method, it can help you to explore the structure of the data, or can also be used as a dimension reduction method. All right, so then last time we explained that K-means algorithm in great detail. Right, so if you recall the K-means algorithm, we talk about that, right? How it works, what's its design, and what's the objective function, right? And then what's the problem with this objective function, and then how can we come up with an algorithm to quickly find a solution to that objective function. And then the solution, how does that algorithm work, right? Why it works, why it can help us find a reasonable solution to that optimization problem. But then what's the limitation of this algorithm? Last time we talked about it, it's the so-called greedy algorithm, right? So it's still heuristic. So in that sense, what it finds eventually could be a local minimum rather than a global minimum. So how to overcome that limitation is by trying multiple random starting points, right? So and then we talk about how to find this K parameter, right? So that, as you recall, we said that as K increases, the objective function's value always decreases. So you cannot simply just compare which K gives you the lowest objective function value. Then you end up with the largest possible K value, right? So instead, you should put that into this cost-benefit analysis. Right? Increasing K will decrease the objective function by a little bit, but incur associated costs. So only when the decrease in the objective function value exceeds the cost, right, the threshold, will it be worthwhile to increase K. Right? All right, so but if the benefit falls below the threshold, the cost threshold, then you should stop. All right, so that's how you find the optimal. Okay, and then we can do that easily using this visual tool called the algo chart. All right, so again, that's just quickly talk about. All right, then let's talk about the next cluster analysis method. It's called hierarchical clustering. It takes a different approach. We already talked about the basic setting before the break. So hierarchical clustering, what we want to do is that we want to run this algorithm, which eventually will give us something like that. This is called a dendrogram, right? It's like a tree. It's like a tree. It's an upside down tree. How did we create this dendrogram? By running this algorithm. The outcome of this algorithm naturally give us the dendrogram. Okay, once the algorithm completes, the dendrogram is there. Alright, so it's just a natural reflection, natural kind of a visual summarization of this algorithm output. So what we're going to do, let's quickly review this how this algorithm works. What we're going to do is that basically we merge those data observations into clusters. Alright, one by one. So what we're going to do is we start with the case where each data observation, each data point is one cluster by itself. All right, so then initially we will have n clusters, n equal to the number of data observations that we have. Okay? And then what we do is that among those n clusters, we find that we calculate all pairwise distances. Pairwise distances between any pair of two clusters, we calculate the distance. And we calculate all possible pairwise distances among all these n clusters. And then we pick the pair with the shortest distance. We pick the pair that are close, that is close to each other. The two clusters that are close to each other. We pick that pair of clusters and then we merge them into one cluster. All right, and then we mark that on this dendrogram. The dendrogram, the merging point is the height of the merging point is the distance between the two clusters where they are merged together. All right, this is the dendrogram. And then after this is one iteration of the algorithm. So after this first merger, then we only have n minus 1 clusters left. Then we run the algorithm for the next iteration, for the next time. And then among these n minus 1 clusters, we further calculate all pairwise distances. And then we pick the pair of two clusters that are closest to each other among all pairs. And then we merge this pair of two clusters into one. Again, we mark that on the dendrogram, for example, this one, right? So this is the next closest one. Then we mark them on the dendrogram at the height where that is equal to the distance between the two clusters. All right, so then as a result, the number of clusters is has become n minus 2. And then we run the next iteration again. Among these n minus 2 clusters, we further find the pair of two clusters that are closest to each other and then merge them. And then we keep doing so. And then we mark them on the dendrogram using the height of the merging point as the distance between the two clusters where they are merged. And then you keep doing that. And then the number of clusters, that becomes fewer and fewer, right? You keep merging, more and more data points together. Number of clusters become fewer and fewer. Eventually, you only have 2 clusters remaining, and then you merge these 2 clusters into one, right? And the height is the distance between these 2 clusters. And then the algorithm stops. And then you have a dendrogram fully constructed. All right, so that's the algorithm. So then, once the algorithm is run, is done, then how can we utilize it? With this dendrogram, we can easily cut the tree at different height to get different number of clusters. All right. For example, if we cut the tree here at this height, basically we just draw a horizontal line at a certain height to cut the tree. All right. And then, depending on this horizontal line, how many branches this horizontal line intersects, we have the corresponding number of clusters. So here, this horizontal line, if it's cut here, we intersect 2 branches, right? And then we are having 2 clusters, right? So then the first cluster contains all the leaf nodes that belong to this particular branch. And then the second cluster contains all the leaf nodes that belong to the second cluster. All right? So all the leaf nodes belonging to one branch, that indicates all the data points assigned to that particular cluster. Then all the leaf nodes belonging to the second branch indicate all those data observations assigned to the second cluster. That's how we get cluster assignment based on the data. Right? Of course, if you want more clusters, if instead of 2 clusters, if I want 3 clusters, what should I do? I lower the height where I cut the tree. Right? I cut the tree at a lower height. For example, if I cut the tree here, then it will intersect 3 branches. As a result, we're going to get 3 clusters. All right? So you can keep lowering the height to cut the tree, to get different number of branches. Okay. So of course later, for those who have already worked on the homework calculus, you should see that in R, you do not need to kind of manually determine the height at which you cut the tree, right? So you can just simply specify how many clusters I want, and then the algorithm, the function will find the right height to cut. Basically, you can cut, for example, if you want 2 clusters, you can cut at any height above this level. All right, any height above this level, then you're going to get 2 clusters. And if you want to get 3 clusters, you can cut at any height between this level and this level. All right, but in the R, in the function that we use, you only need to specify the number of clusters that you want. You will find the right height for it. All right, so that's the algorithm. That's the overview of the algorithm. So then let's talk about one key issue, right? So actually, we already quickly discussed that before the break. So we already talked about that how to measure the distance between 2 data observations, 2 data points. We already talked about that, if you recall, right? The most common approach, the most common distance measure is this so-called Euclidean distance. We measure the distance between 2 points, right? Just like we measure the distance, the geographical distance between any 2 points in the 2-dimensional geographical space, right? We use this, this Euclidean distance. We require explain that time in class, right? So it's like the longitude and the latitude, right? So then the coordinate of any point geographically, and then 2 points, then you just measure the distance using the difference between each coordinate, and then square, and then sum, and then take the square root. Okay, square root of sum of squared difference in each coordinate, each dimension. Right? So then that's the distance, that's the Euclidean distance. And then we can easily extend that into measuring the distance between any 2 data points, each of which involves multiple dimensions in terms of their x variable values. Right? So you have multiple x variable values. Each value is like a coordinate along one dimension, so it's multi-dimensional coordinates. And then it's just a natural extension. Right? So just a sum of squares, and then take a square. So it's already clear. So, but what's new here? This distance we also use that in the K-means algorithm, right, to measure the distance between any 2 data points. Then what's new here is that for the hierarchical clustering algorithm, we also need to, in addition to measuring the distance between any 2 data points, we also need to measure what? Distance between any 2 clusters, each of which contains multiple data points. Right, then how to measure the distance between 2 clusters as 2 collections of data points. Right, so we need a different measure. So that's the so-called linkage. All right, so then we have different choices of possible linkage to use. Right, recall that we actually quickly discussed that. What's the most kind of intuitive approach to measure distance between 2 clusters? Center to center, exactly. Center to center, that's called a centroid linkage. We find the centroid of the 2 clusters and then measure the distance between the 2 centroids. Each centroid is like 1 data point. Then we just use the distance between these 2 data points. Right? We use the usual Euclidean distance measure to measure the distance between the 2 centroids, the 2 data points, and use that distance as the distance between the 2 clusters. That's the centroid linkage. But of course, we have other linkage that we can use. Single linkage. We calculate all pairwise distances across these 2 clusters. And then we find that we use the shortest pair. Use that distance as a distance between the 2 clusters. That's one approach. This is called a single linkage. Right? Remember, we use this one. Right? So this is this graph to represent it. each of these two countries can represent one cluster. Then that all the data points within these two clusters, and then we calculate all the pairwise distances across these two clusters, and then we find the shortest pair. Use that distance as the distance between these two clusters. If that's the approach that we take, that's called a single linkage. Right? And then alternatively, we can use the longest pairwise distance across these two clusters as the distance between the two clusters. If that's the approach that we take, that's called the complete linkage. Right? Yeah, centroid linkage is what we just talked about. Find the center point, the centroid of the two clusters, and then measure this. That's called the centroid linkage. Of course, there's another linkage called the average linkage. Average linkage, how do we do that? Calculate all pairwise distances across the two clusters, and then take the average. Use the average of all pairwise distances as the distance between the two clusters. All right, so these are the four commonly used linkage approach, linkage measures that we can consider, we can choose. Okay, now the next question is that what's the pros and the cons of those choices? Which one performs the best? Which one we should choose? Which one we should avoid? All right. So one thing I asked you last time, if you still remember, is that think about it. When we use those linkage to measure the distance between two clusters, and when we run that algorithm, hierarchical clustering algorithm, and then constructed the dendrogram based on the output, can we guarantee that a later merger always happens at a higher height than the previous merger? Can we guarantee that? Actually, the answer is it depends on which linkage you choose. All right, so some linkages we have that feature, but some linkages cannot guarantee that feature. So let's think about that. Which linkage will be problematic? Which linkage will? Let's consider a very simple example. We don't need to do the formal proof, but just like a very simple example. Let's only consider like 3 data points. 3 data points. We want to perform this hierarchical cluster. Right? So then how does this algorithm work? First, we start with 3 clusters. Right? Each cluster is 1 data point by itself. And then we calculate all the pairwise distance and then find the shortest pair. So we calculate all the pairwise distance. And then find the shortest pair. Which one is the shortest? This one is the shortest, right? So then in the first iteration, we merge these 2 points into 1 cluster. All right? And then this is still the cluster by itself. So then after the first iteration, we have those 2 clusters remaining. All right? And then second stage, we merge these 2, right? Because there are only 2 clusters remaining, so we just merge these 2 and the algorithm stops. Now my question is, at the second merger, the distance between this cluster and this cluster, is that guaranteed to be always smaller than the distance between these 2 clusters, between these 2 data points? This is the distance at which the first merger happened, right? This is the distance, this distance between these 2 clusters is the distance where the second merger happens. Right? Can we say that this distance is always larger than the distance between these 2? Yes. Well, depends on which linkage we choose. Let's say if we choose single linkage, do we have that feature? What is single linkage? Single linkage is the shortest. So the first merger doesn't matter, right? Because it's just between the 2 data points. So that we just use the standard Euclidean. The linkage, when linkage matters is the second merger. When we merge this one and this one, because this one now is a cluster, right? We involve 2 data points, so we need to use the linkage. So the single linkage is simply measure the pairwise distance between this one and this one and this one and this one, and then we choose the shorter one as the measure of the distance between these 2 clusters. So let's say which one is shorter. So this one and this one is shorter. So we're going to use this one. So use this distance as the distance between these two clusters. All right, now think about it. Is distance guaranteed to be larger than this one? Yes. Why? Because otherwise, the first merger wouldn't merge these 2 points, wouldn't merge the other two, right? So it must be, this one must be the shortest, this one must be shorter than this one. So you see, single linkage can guarantee that the second merge actually happens at a larger distance than the first one. All right, so how about complete linkage? Same thing. Complete linkage, you want to use this one, right? The larger one. So the larger one should still be, be further larger than that one. So complete linkage is also good. How about average linkage? Also good. Average linkage, use the average of these two distances as the distance between these two clusters. Because each of these will be larger than this one. So the average will also be larger than that. Okay? Average linkage also good. How about centroid linkage? You see, centroid linkage is problematic. Centroid linkage, how do we do that? We find the centroid of the cluster, right? The centroid cluster, and we use this distance as the distance between the two clusters. Now, is this distance guaranteed to be less than this one? Not necessarily. All right, you can think about it like a, high school geometry, right? So it's not necessarily. Okay, even if these two edges are all longer than this edge, but no guarantee that this one is definitely longer than this one. No guarantee. It could be smaller. All right, so this is why this centroid linkage could lead to this so-called inversion problem. What is inversion problem? A later merger happens at a lower height than a previous merger. All right, inversion problem. So when draw on this dendrogram, how will inversion look? You see a later merger, for example, a later merger here, it could happen at a lower height than the previous merger. Previous merger happened at here, right? A later merger could happen at a lower height. So as a result, you're gonna see the later merger, happening here. So, on the graph, what we often draw is this way. You see, the later merger happened here, but the height instead of here, it's here. It's the inversion. Later we're going to see that in the output. So that's the inversion. So inversion is, apparently makes this whole dendrogram very weird, right? So it's not a favorable property. So it's something that we want to avoid. So although centroid linkage is probably the most intuitive measure of distance between two clusters, but because of this problem, so we usually avoid this centroid linkage. So another linkage that could be potentially problematic is single linkage. Single linkage may lead to the so-called trailing cluster problem. So as a result, you're going to see, if you draw the dendrogram of from single linkage, you'll see that the cluster are expanded like every time by absorbing one new data point. So you can see the cluster, the dendrogram looks like that. It's not well balanced. It's keep observing those cluster, the tree, right? The cluster is formed by keep absorbing one new data point at a time. All right, so as a result, it's like a chain. It's the cluster is like a chain. It's called a trailing, cluster problem. So the cluster formation is not well balanced, and as a result, you tend to have those like a singleton cluster left. All right, so you may have like a 4 clusters. 3 of them contain like by absorbing all those data points, but then the last cluster, the 4th cluster, is one data point by itself. You see the output of single linkage is oftentimes not well balanced. So that's also something that we want to avoid. All right. So overall, complete linkage and average linkage works better. Right? And then compare these two, actually complete linkage is even better. Because complete linkage is, it's based on the relative order. So it's less sensitive to the metric that you are using, to the unit, to the metric of the distance that you are using. So this is even more robust. All right, so, complete linkage and average linkage, what choices I think here. Right, so that's the linkage function that we can use. Right, so that's about that. So that will complete our discussion of our description of this hierarchical clustering algorithm. Right, so we know how the algorithm works, and also we know how to measure the distance. Right, and the whole algorithm is very fun. Okay, now think about that. Comparing k-means and the hierarchical clustering. Again, what's the pros and the cons? Which one is better? Which one do you like better? The good thing about hierarchical clustering is that it's sort of more intuitive, right? It's more kind of you can visualize that, right? You have this tree structure, you have this dendrogram structure available after the algorithm, and then you do not need to pre-specify the number of clusters, right? And you can, given the tree, you can sort of cut the tree at any time. So those are the advantages of hierarchical. But what's going to be the potential disadvantage? Think about it. In terms of computation, which algorithm is more intensive? Which one computes more? This one, hierarchical cluster. Why? It needs to calculate all pairwise distances. Right? That's a lot if you think about it. You have n. Out of n, you can compute all pairs of 2. Right? This is a large combination number if n is huge. All right, if you have millions of records, it's n times the combination of 2 out of n, right? Out of like 1 million. So that's a lot. So that's on the scale of n squared. All right, so that's actually a lot. But in comparison, how many calculations do you need to do in k-means algorithm? K times n, right? So because every time you do that, you recall in k-means algorithm, what do you need to do? You only need to calculate the distance between each data point and the cluster, the centroids of the k clusters, right? So there are only k centroids, and then times n. So that computational, the complexity is k times n. But k usually is a much smaller number, right? It's a smaller number. It's a single digit usually. So although n is large, but the computation complexity is actually one kind of order lower, right? So instead of n squared, it's only like on the order of n. All right, so that's why k-means algorithm actually is less computational intensive. So that's why for large data sets, and especially if you want to do real-time analysis, you want to generate output right away, you needed some speed. You have some requirement for the speed of calculations. Actually, k-means algorithm is a better choice. All right, and another important limitation of this hierarchical clustering is that it's due to its structure by design. Now think about that. Given this algorithm, the nature, the structure of this algorithm, what can we say about the resulting cluster assignments? Let's say if I get 2 clusters, and then I move on to increase the number of clusters by 1, and then as a result I get 3 clusters. How do the 2 results compare? The cluster formation from 2 clusters versus the cluster formation from 3 clusters. What's the relationship between these 2 results?
One of the clusters will split in 2.
Exactly, right? It's always the case. You see, if we get 2 clusters, that will be this. If I want to increase the number of clusters, what am I going to get? Just split one of the previous 2 clusters into 2. All right, same thing. If I want to further increase the number of clusters, increase that into 4, what am I going to get? Just split one of the current 3 clusters into 2. All right, you keep increasing the number of clusters. You're gonna keep splitting, keep dividing one of the existing clusters into 2. That's always the structure. So this is called the nested structure of this hierarchical algorithm. The cluster, they are nested together. Now think about it. What could be a potential limitation of this nature? Now think about that. If I want to, there's some analysis, right? A lot of data, a lot of variables. So say if I want to group all the customers into two classes, maybe there is one variable that's best suited for that division, for that separation. Let's just say like a random thing, maybe for customer, individual customer, maybe gender is the best, like a variable to divide all customers into two parts, two segments, right? So that their shopping behavior, purchase behavior will be different across male and female customers. But if I want to divide all the customers into three classes, maybe a totally different variable would be the best variable to use to separate them, right? Maybe income level. You see, so as a result, then the cluster formation could be totally independent across these two cases. When I try to cluster everything into two classes versus when I try to cluster everything into three classes. The way of doing the separation, the segmentation could be totally different. That's possible, right? But this will not be possible under this hierarchical clustering. Because hierarchical clustering, the outcome will always be like that. If you want a 3, I just divide one of the previous 2 into 2. Alright, so it will not be facilitated by. So if you run this hierarchical, you will not find those outcomes as I just said. Or if you want to now do 2, 3 sets, then you completely retry. Completely starting from the beginning and redo the clustering analysis into 3 classes. You will not be able to do so based on hierarchical. But k-means will be able to enable us to do that. Think about it. The k-means algorithm, do we have any restriction about that? What happens if we increase k from 2 to 3? We're going to restart from the beginning, right? So from all the data points, and then we redo them, into clustering into 3 clusters. We will, from the very beginning, we will just consider 3 clusters and find the 3 centroids, right? And then the 3 assign, and then just group them. So then k-means will enable us like a complete kind of reshuffling, right? If we change the number of clusters. So that's the kind of the limitation of hierarchical clustering, and that's the benefit of using k-means over hierarchy. And actually, another limitation of hierarchical clustering is that it's actually less stable, to the data. So if you add more data points, or if you remove some data observations from the data set, the tree, the dendrogram that you're going to get could be quite different. So it's less stable. All right? So that's why overall, k-means is actually a more kind of a robust, it's a more reasonable choice. That's why actually it's more kind of commonly used cluster analysis. All right. Okay, so that's the comparison between cluster k-means and hierarchical cluster. So finally, some final words about the general kind of considerations that we need to keep in mind when we perform cluster analysis. First thing, for those who have already worked on the homework exercises, you should be able to kind of see that result, right? So the first thing, can we simply just use the variables by themselves in the original measures to do cluster analysis? We need to be careful. Oftentimes there will be some problem. The problem is that some variables, their values are very large. Right? For example, in the homework exercise, you can see that so for example, we consider 2 variables. One is the monetary spending. One is the number of visits to the mall. Then monetary spending is typically, in a large value, right? So on say a scale of hundreds or even thousands. But the number of visits is usually single digit. Right, 1 or 2, very small values. Then if we just use these 2 variables, these 2 variables in their original values, and then do the cluster analysis, what are we going to get? Think about that. When we do cluster analysis, we measure distance. How do we measure distance? See, like that. Right? But if one variable is at a much larger scale than another variable, what will happen? That variable will dominate the distance measure. Right? So the distance between, in that variable, right, will dominate the distance, in another variable whose value is on a much smaller scale. So as a result, then the whole difference, the whole clustering outcome is basically dominated by that variable with larger value. All right, so then all the other variables with smaller values actually they do not really play a role in determining the cluster outcome, which is certainly not reasonable. It's not what we want. Right? We want all variables to play a role, to be taken into consideration when forming the cluster outcome. Then how can we overcome that problem? By doing that scaling. All right, so that's very important. Scale all the variables to normal. Basically, scaling is a normalization, right? So you normalize all variables so that their values will all be on that same scale. So how does scaling work? How do we actually do scaling? In R, you can either do scale with using that scale function. There's just a function called a scale. You just use that scale function and will scale all the variables. But how is that actually done? First of all, the scale function will deeming, the so-called deeming, for each variable. All right, so it takes all the values of that variables in your data set, right, across all observations in your data set. And then it will calculate the mean. For example, say monetary spending, right? So then the mean is say several hundreds dollars, right? So it's the mean of monetary spending across all customers in your data set. And then we calculate the mean. And then it deeming, what does deeming mean? We just deduct that mean from each value of that variable in your data set. All right, so after the deeming, some values may be negative. All right, so it's very normal to see negative numbers. Don't be sort of surprised to see negative numbers. Monetary spending we cannot really be negative. But after scaling, after deeming, you're gonna see those negative values for those monetary spending. But that's okay. That simply means it's below mean. All right, and then that's the first step, deeming. Second step is what? Normalization. You calculate the standard deviation for that variable. Again, across all values, all observations in your data set. Sample standard deviation. And then you divide each value by that standard deviation. All right, this is a normalization. So after that calculation, what are you gonna get? Now all the normalized values will have standard deviation equal to 1. All right, so then you're gonna also do the same scaling for all the other variables. So then after all the scaling, then all variables now will have mean equal to 0 and the standard deviation equal to 1. So they will be completely the same scale. And then you can measure them. You can incorporate them into that distance measure. And then all of them will contribute equally to the determination of the distance between any data point. And as a result, all of them will contribute equally to the final determination of the cluster outcome. All right, so that's why scaling is very important. That's the important part of doing cluster analysis. Before cluster analysis, we always scale all the variables and then feed them into the cluster analysis. All right, of course, then we have a lot of choice of different variables, determining the stability of the outcome, and also try to make sure that the outcome you get are so-called robust. Robust means it's consistent across different choices of parameter values or even different choices of methods. All right, so we talk about this two cluster method. You can try both, right? For the same data set, you can try both. You can try both k-means, and then you can try hierarchical clustering. And then at the same number of clusters, are the outcome so-called robust? Are the outcome consistent? Roughly the same. If the outcome across these two methods change a lot, differ a lot, that means at least one of them is not really robust. It's not really representative. So then you need to think about it. How much can you trust, right? Each of these outcomes. But if it's robust, it's pretty much stay the same. Then you have more confidence in kind of reading into those outcomes. All right. And also try different choices of parameters, right? For example, linkage function, right? So as we said, some linkage function we want to avoid, right? But some linkage function, the complete linkage and average linkage, we can try both and see if the results are reasonable, are robust or not. If they are robust, then again we can have more confidence in just using those results, in trusting the implications derived from those results. All right. So finally, after we get all the clusters, that's actually just the start of our analysis, start our kind of the implication derivation. Then you need to look at those clusters, all those cluster elements, and then you try to interpret them. That's very important, right? Then what does each cluster represent, right? So for example, if we're doing customer-consumer segmentation, then okay, we found the 3 clusters of consumers. Then what do they represent? What kind of is the typical consumption pattern associated with each cluster? Those are the things that you need to think, you need to do. So interpret those clusters. Ideally we want to come up with some label, some shorter description to label each cluster, right? So those are like, heavy spender, those are like a frequent visitor, those like come up with a short description to label each cluster. And then you can further perform your analysis, right? If you want to do kind of a targeted promotion, you want to do kind of a personalized strategy, customized strategy, you can do that. Since, based on the features of each cluster, right? You think about the best, the optimal strategy to be designed, to be applied to each cluster. Right. So in this sense, cluster analysis usually is the starting point of some subsequent analysis, rather than the ending point, rather than the final analysis. All right, so usually it's like the first step, try to understand the data, and then you lead to the subsequent more sophisticated analysis afterwards. Then also, because it depends on sensitive, it depends on all those choices, all those different parameters. So usually take the results of cluster analysis with a grain of salt, right? Rather than as like absolute outcome, because when we choose those different parameter values, the exact clustering outcome will change a little bit. Alright, so that's what we want to talk about for cluster analysis. So I don't want to spend too much time to go over all the details. Again, you can always watch the video for details. But just like let me quickly point you to some outcomes in R, some key points in R that you need to pay attention to. This is the demonstration video demonstration example that I use, right? So we can do the k-means cluster and also hierarchical cluster. For these 2 clustering methods in R, we do not need to install any external package. Actually, those methods, those functions are already incorporated in the core R installation. One is called the k-means, simply called the k-means. That's the k-means algorithm. And another one is called the H cluster. That's for the hierarchical cluster. All right. So let me quickly show you how to do hierarchical clustering. So hierarchical clustering, first of all, you get the data set, right? So then, you see, we need to do scaling. You see, this is the original data set, right? But we can just scale that, use this scale function to scale the original data set. So let's take a quick look at the scaled data set. You see, these are the scaled values, right? So these values, you see, first of all, you see positive and negative values. They are centered at 0, right? And then you see the scale. They are all on the same scale. Okay, they all have, each of these 2 variables now all have standard deviation in 1. All right, these are the scaled values. First, let me show you this. These are the original values of the 2 variables we used here. You see, totally on a different scale, right? The first variable has a very large value. Second variable has a much smaller value. But after scaling, right, they look like that. These are the scaled values. All right, all consistent. So all on the same scale, all centered around 0. Right? So that's it. So all the analysis, all the cluster analysis need to be based on those scaled values. Right? All right. So what we can do here is that we can do this hierarchical clustering. All right. So let me quickly show you the output of hierarchical. Use a scaled value, and then we can simply specify the method using which linkage we want to use. Here, if we specify average, that means we want to use the average linkage. And then get the clustering outcome and save that into a variable. Right? Now, how do we plot that on the plot? To plot the hierarchical clustering outcome, the dendrogram, actually we can simply use this plot function, the usual plot function. But here, this plot function is not actually the usual plot function. The usual plot function will plot what? Scatter plot. All right, so that's the standard, the default plot function. But here, if we call plot to plot some output from the H cluster function, actually this plot function is a different version of the plot function that has been redefined by this H cluster by that object. So that's it's the plotting of the dendrogram. All right, so that's why we can simply call the plot function, but it will plot the dendrogram for us instead. All right, so this only happens when we pass in an object and the result from this H cluster function. All right, so then the dendrogram looks like that. Right, so and then we can cut the tree. So here in the homework exercise, I asked you to add a horizontal line explicitly at a certain height of your choice, just to get the number of clusters, the kind of the pre-specified number of clusters. Right, this is just to help you kind of see, okay, how this whole tree cutting works. But in the real application, you don't need to do that. All right, that's only for the exercise purpose. In the real application, you do not need to do that manually for that. So what you do instead is this cut tree. Use this cut tree function. All right, cut tree, passing the hierarchical clustering outcome, and then you specify the number of clusters that you want. And it will automatically cut the tree for you and get the associated cluster assignment for you. All right, so that's something. All right, let me quickly also show you how to get this up. You see, this is the hierarchical clustering from this average linkage, right? Let's quickly look at other linkage. This is from the central linkage. Take a look at the central linkage. You see, this one. You see, what does that mean? You see, this one. What does that mean? That means, you see, this merger happens at this height. But this later merger here, when we merge this one and this one, it happens at a lower height than this merger. Is that clear? You see, this merger, when we merge this and this, right, these two clusters, this happens at this height. But then later, at this merger, when we merge this one and this one, it happens at a lower height than the previous merger. This is what we talk about. This is the inversion that we discussed.
So what is the implication of the inversion?
Yeah, it's just like I said, the next merger happens at a lower distance, lower height than the previous merger. So just because of your design, your choice of distance measure. So it happened to be. It's not supposed to be like that, right? Because we're supposed to merge something closer to each other first, and then merge, do the next merger, we merge something farther from each other. But because of that choice of this distance measure, the central distance measure, basically just theoretically, mathematically, there's no guarantee of this problem. So which is not favorable, which is not intuitive. No, like a very intuitive interpretation of this. Right? We shouldn't see this approach. So that's why this inversion is something that we want to avoid.
Is it meaning that the one that happens earlier, it's basically saying the distance between those points is greater than the distance between the merger that's supposed to?
Exactly, the distance here is greater than the distance between the later merger. You see, the previous merger, when we merge this and this together, right, that distance is greater than the distance between this one and this one.
So you cut it below the inversion.
Mhm.
Does it give you 2 clusters or 3 clusters?
That's the same thing as before. If you cluster at a certain, yeah, that's actually a good question. So we can try. Yeah, you can try. We can try. We can try find the. Yeah, but of course here we need to find the right height to cut. Right? So you have to between this one and this one. Yeah, it's a very small interval. Yeah, we can try to find the cut, the height, and then see what we're gonna do. Yeah, I mean we can try that later on. So it takes a while to find the right height. So for that cut tree function, you could also try to specify h instead of k. You specify k, that gives you the number of design the number of clusters. But you could also try h equal to a certain value. Then basically you just want to cut a tree at that height. All right. So yeah. So I'll leave that as an exercise to you. So just find the height, the right interval, right, between these two, and then you run this cut tree. You cut that tree at that particular height. See what clusters that you get.
You have inversion, you're trying to decide how many pieces there are by cutting the tree. Could you just manually decide where to put the offending one so that you can just determine the right number of clusters?
Yes, if you want to, if you want to test that, of course, you can always figure out where you want to cut the tree. You can cut the tree at any height you like. All right, so but if you want to, just find the offending one, then you just cut at that particular range. See what you're gonna get. My suspicion is that it shouldn't get the other one, because then it will not be logical. You should only intersect because you intersect this one, so then you cannot further, right? Because you intersect this one, then it contains everything of that one. Then you cannot further include these two. You see? Yeah, but of course, we can always test. Yeah, but again, I'll leave that to you at the next test, right? So find that small interval out of this output, and then cut the tree at that level, and see what's the cluster now. All right, so that's one thing that, of course, we can also show the diagram on other linkage, but the other linkage behave a little bit normal. Let me show you this single linkage. Single linkage, you can also see that it doesn't look so balanced, so well balanced. You see, it has this trading. Every time it absorbs one single data point into that, it's like that. It tends to have a trading pattern. But for this one, it's less obvious. But for some data sets, the trading pattern is very obvious. Every time a larger cluster will observe one more singleton data point into that. Complete linkage looks more balanced. It seems more kind of well balanced. Right. Okay, another thing that I want to quickly point out is that how do we plot the clustering outcome here on the plot? We use those color code. Okay, so different cluster. So eventually, what cluster outcome do we get? Just a cluster assignment. For each data point, you get one cluster assignment. For example, if you want 3 clusters, then you get 1, 2, 3, right? So the label. So then for each data point, you get, the assignment of one of the 3 numbers. Okay? So then what we're gonna do is that how do we visualize the clustering outcome? We're gonna use this cluster analysis, those cluster assignment as the color code. That's the kind of the trick that we are using here. You see, when we plot that one, here, in this usual plot function, all right, when we plot that, we use this color, COL. That's the color argument. That's for the color code, the code for each data point in your scatter plot. So, but you see, what color code do we supply? we supply the outcome from this cut tree function. The cut tree function will give you what? A vector of those cluster elements for correspond to each data point in your data set. All right, so in your data set, for example, if you have 1,000 data points, then this cut tree will give you a vector of 1,000 integers. Each integer is one of the three numbers, 1, 2, 3, correspond to the three clusters that you want. All right, so it gives you 1,000 of this cluster numbers. And then we simply use those cluster assignment, those cluster number as the color code. So for those data points assigned to cluster 1, they will be marked in color coded 1. Okay, for those data points assigned to cluster 2, they will be marked in color coded 2. As to what the color code 1 means, what the color code 2 means, what colors we're gonna get, we don't really care. It doesn't really matter. As long as they are marked in different colors, we'll be able to see the clustering outcome. You see, that's the key kind of a trick that we use to easily visualize that clustering outcome. So it's also the same thing when we do the clustering outcome based on the K-means algorithm. Right? The K-means algorithm, the cluster assignment is stored in this cluster, this object. All right, so we just extract that object and again assign that to the color COL, that argument. So the same approach. All right, so let me quickly show you. Another thing that we want to do is this one. This MF row. It's called a multi-frame by row. So basically, you can split this entire display panel into sub-panels. All right, so this will allow you to display rather than only one single plot, but multiple plots at the same time for you to do easy comparison. This is also a very useful trick to do. All right, so here these two numbers are the number of rows and the number of columns to split this display panel into. So if we do 1, 2, that means we want 1 row and 2 columns. So basically just 2 plots side by side. But you can do 2, 2, then you split this window into 4 panels, 2 by 2, 2 rows by 2 columns. All right, but don't forget, once you've done that, if you want to restore the single plot display, you need to do reset that to 1, 1. All right, because otherwise it's always divided into the into the multi-panel. All right, so let's here if we run this one, and we want to divide the window into 1 by 2, basically just 2 subpanels, and then we can display. And about that, I didn't run the K-means algorithm, so there's no problem. You see, if I had the K-means algorithm, its result will be displayed here, and this is the result from the hierarchical algorithm. Let me restore that. Alright, let me just quickly show you the hierarchical cluster. Alright, for the homework exercises, you just need to do something like that. Alright, so for this one, for this demonstration example, as I explained in the video, we only have like a small number of observations, and each observation is a company, it has a name. So that's why I also display the name of the companies on the plot, so that you know which one is which. But that's only for this example, because it has a small number of observations, and also because each data point, each observation has its unique identity, which is meaningful to us. But for the homework exercise, we are just dealing with customer, right? Each customer basically just have an ID. The ID is not really meaningful, right? So, and also we have so many customers. So no point of displaying those labels, those names on the plot. Simply just display the point itself. That's it. All right. So for the homework exercise, just skip that the text, that function. No need to do that. All right. So anyway, let's just take a quick look at it. Right. It's something like that. All right. So these are all the original data points. For that, and then we mark them in different colors based on the cluster numbers. Here we are getting 4 clusters, so we display all the data points in 4 different colors. Okay, based on their cluster. And also another thing to keep in mind is that for the plotting here, what we're gonna plot is we're gonna plot based on the original values of the variables. All right, we do cluster analysis based on the scaled values. But when we plot that, because eventually still the original values matter, right? All the implication or the visualization, we should still base on the original values of those variables. That's also something to do. All right, so it doesn't matter. So because all we want is the cluster assignment associated with each data point. Okay, that's what we want from this cluster analysis. But that is based on the skilled data. But then when we do the plot analysis, with the plot, we still feed in the original unskilled data, all those data values. And then we mark those different data points in the corresponding cluster alignment using the corresponding color code. All right, so you do not need to do anything special to kind of restore that. You just feed in supply the original data into the plot function, but then just use the cluster alignment as the color code. All right, so that's the key parts that you need to do. And then once you've done that, I also ask you to try different options, right? And see the results are robust or not. And then just based on those clustering outcomes, just try to interpret each cluster, right? Come up with a label to describe each cluster and and think about what you can do, right? So if I want to say do a targeting promotion, right? Which one do you think is the best segment to target, to kind of boost your revenue sales rate, things like that. All right, that's all we want to talk about for cluster analysis. Okay, so let's now start the next topic. Next topic I want to talk about is also part of this, is also like one type of this unsupervised learning method. So this actually falls into this big category called association detection. All right, cluster analysis is doing the cluster, right? So trying to group data sets, data points into different sets. But association detection, performs a totally like a different analysis. Association detection basically just try to find some association or correlation between variables. It's very simple. And the leading example of association detection is actually the so-called market basket analysis. Market basket analysis actually is very simple. It's just look at what customers purchase, say in a grocery store or nowadays, on the online digital e-commerce platform. And we look at what customers tend to purchase together. We look at the checkout data of customers and look at what they tend to purchase together. Again, the original application is in the usual grocery setting, the supermarket setting, right? You look at the so-called the scanner data, just the checkout data, every time customer in their shopping cart, right? What items do they buy together? And then we just want to find that the answer to that question. What items customers are most likely to buy together? All right, and then that's the market basket analysis. That's the leading example of association detection. So think about it. What could be, what could be a potential kind of a meaningful implications if we find out what items customers tend to buy together? You can promote the so-called cross-selling opportunity, right? If some customer if you know that these items are most likely to be purchased together, then if you find the customer has bought one item, you can promote the other item. And very likely that customer will also be interested in that item. Right? This is called a cross-selling promotion, cross-selling opportunity. And then, in supermarket, you see they do a lot of analysis like that, so that they can arrange the shelf space, right? Kind of optimally, so that those items tend to be purchased together. They can be arranged close to each other. Then customers are easy to find those items, and then again they can buy more. Right, and on the online platform, you find all those recommendations, right? So if you find that one item, we're gonna buy more. It may also be, once you put one item into the shopping cart, you'll be recommended with the other items. All right, so that's the lead example. But of course, the basic version of that market basket analysis actually is pretty kind of straightforward. That's why I want to skip that part, because it's basically just calculate the correlation. Okay, so it's just a conditional kind of dependency. It's the conditional probability. It's just a probability. Conditional on this item being purchased, what's the probability of the other item is also purchased. So it's just basically a very simple application of conditional probability. All right, so that's why we're not going to talk about that. But instead, we're going to talk about a more sophisticated version. It's also trying to look at what items, right, tend to be sort of purchased or tend to be liked together. But it's not only based on like a single, like the overall item, but instead we will based on, how similar other customers are to this particular customer, so that we can provide personalized recommendation. Not only like in general, these two items are purchased, are often liked together, but instead we provide personalized recommendation for you. What is likely? What items? Are you likely to like? All right, but for a different customer, we may provide a different recommendation. So personalized recommendation. This actually is enabled by the method that we are going to talk about next, so-called collaborative filtering. All right, collaborative filtering actually it's behind all those applications that we encounter almost every day. So you go to Amazon, right? You purchase something, it will tell you what you see on the screen. People who purchase this item or people who like this item also like these items, right? And when you go onto the Netflix, right, you watch some video, you give them a high rating, and you'll be recommended with other videos, right? Other movies, basically saying people who like this movie also like these movies. Again, these recommendations, like I said, they are not like a general, common recommendation. It's personalized recommendation. It's based on your past purchase behavior, based on your past rating history, based on your own preference. So every different user will see a different recommendation. All right, so that's why I said it's beyond the basic version of market basket analysis. Basic market basket analysis look at overall what items are likely to be purchased again. All right, so it's just the common calculation. But this one, the collaborative filtering actually will enable the so-called personalized recommendation. Now think about it. How can that be done? Or how would you do that? Say if you are tasked with that task, just to provide a personalized recommendation to each customer based on his or her, past kind of a rating. Let's say rating history, right? You know that customer has rated those different items. This particular customer likes or dislikes certain items, and then you see all the ratings of all customers on your platform. Then how can you provide personalized recommendation? How can you predict what items are most likely liked by this particular customer? How would you do that? Roughly, what will be the approach?
You look at customers with similar likes, and then you assume that this customer will also like those same sorts of things.
Exactly, right? So that's the right direction. We look at other customers' preference and find those customers who are similar to this focal customer in terms of their preferences, in terms of their reviewed preferences, right? And then we look at what other items other customers also like, but this customer hasn't experienced yet, and then we recommend those items to this customer. All right, so that's the general approach.
Should we also look at how similar each product is between them?
Yeah, excellent. That's another possible approach. Another possible approach is that we look at the products. So that's actually exactly the two approaches that we can do for collaborative filtering. One is called a user-based collaborative filtering. The other one is called item-based collaborative filtering. That's exactly just looking at the two different associations. One is from the customers. We find the customers who are similar to this focal customer. But on the other hand, we could also do that item-based. So we find items that are similar to this focal item. And so anyway, we're going to talk about the details later. So, but first of all, the name, right? So this approach actually is also suggested consistent with the name of this method, collaborative filtering. 2 words, right? Filtering means what? We want to provide some recommendation. We want to filter. There are large number of items available on this platform, right? Certainly, we do not want to recommend everything to this single customer. So we want to do some filtering. We only want to recommend a short set of items, right, that are most likely to be liked by this customer to each customer. So this is what the filtering is about. It's about recommendation, right? Filtering only recommended the most relevant information. And why it's called collaborative filtering? Why it's collaborative? It's based on other customers. So basically customers, right? So they are like helping each other. So we look at other customers, review the preference, and use those information to help this vocal. So that's what collaborative filtering. All right. So as a result, you're gonna get is that personalized, a real personalized recommendation. Each customer is gonna get a different recommendation based on his or own preference. Of course, what information we can utilize, actually, a lot of different information we can utilize. Depend on context, and depend on what you are interested in your particular application. So we can use past purchase, the actual purchase, or we can use like just a browsing behavior, like just clicking, right? Or we can use the rating, just the rating, how much I like each item. Right? So, but for our application, just to focus, actually those for those different, activities, different data, the past history that we're going to utilize, we can easily just adapt the algorithm a little bit, okay, to incorporate those different variables. But here, just to fix idea, just as an illustration, we're going to only focus on rating values, just only use rating, each customer rating. So we can think about like the Netflix setting. Okay, so for all the videos that I have watched, right, for each video I give a rate. Okay, I give a rate. And then just every customer does that. And then just based on everybody's rating, and we want to come up with like a personalized recommendation to each individual customer. Right? So then the data that we're gonna deal with is organized in this way. It's very simple data structure. So it's organized in this two-dimensional table, user and item combination. Okay, so then we have each user, right? You can think about it as each row again correspond to one user, and then all the columns correspond to all items available on that platform. And you can think of it, all the movies available on Netflix, right? Correspond to all the columns. And then for each user, for those movies, those items that particular user has rated, then we observe certain value. All right, so basically for each user item combination, it's the rating of this particular user gave to this particular item. All right, and we have a particular value, that's a rating. So, you can think of the rating as on a scale of 1 to 5. But here, what if, apparently, one user only rates a very small portion, small subset of all items available on this platform. So as a result, how will this entire big table, big matrix look? For those user item pair where the rating is not given, the rating is not available, we simply leave that as blank, leave that particular user item pair as blank, leave that particular cell of this big matrix as blank. So as a result, this matrix will be very so-called sparse. All right, so most of the cells in this big matrix will be blank, will be empty. Empty, in the data storage, we simply represent that as a missing value. So there's no value for this particular cell. So as a result, this matrix, this big matrix, will be pretty so-called sparse. So this sparse matrix. So how we actually store those data in the program will not be based on the actual matrix structure, because it will be too efficient to utilize the storage space, because most of the cells will be empty. So instead, we're going to store the data in a special format. So the special format simply just stored all those non-empty ratings. And we simply just record the user ID and the item ID and the rating. You see, just store this entire rating matrix as a series of those non-empty ratings. All right, as the triplet, there's 3 values: user ID, item ID, and the corresponding rating. And that's it. So only record those only record those non-empty, only record those available ratings. And everything else will be just missing. All right, so that's how we store the data. So for this reason, you need to do the conversion. Later, you see that in the R package, right? So you're going to need to do the conversion. The rating matrix need to be converted to the data structure recognized by the package in order to perform analysis. Then the output need to be converted back to the usual data structure in order to be displayed properly on the R. Alright. Now think about that. How can we do this collaborative filter? Right, so we're gonna leave the details of the algorithm next, but think about it. How can we do that? The general approach will be we're gonna have for each customer, right? We observe those data. You know, each user has rated a certain item and has left other items as unrated. Then how can we make a personalized the recommendation? What we can do is that we can predict the potential rating of each of a particular user on certain items that he or she hasn't rated yet. Right? And if we can make such prediction for all unrated items by that particular user, and then we simply pick the item with the highest predicted rating, and then that will be the most recommended item for this particular user. All right, that's the approach that we're going to take. Basically, we can reform this personalized recommendation problem into this way. Just predict the potential rating of each user on all those items he or she hasn't rated yet. And then we pick the item with the highest predicted rating as the most recommended. But then the question is how to make such predictions? Well, we need to look at all the other users' ratings on all those items. Right? If I want to make predictions for user 1 on item 2, what should I look at? All the other users' rating on item 2. Right? But should I treat all the other users equally? Not really. Right? So we should treat those users who are most similar to this focal user kind of more important. To use their rating, give their rating a better weight. All right, but those users who are less similar to this focal user, we should give their rating on this focal item less weight. So that's the general approach. All right, so next class we're going to talk about the details to formalize that. All right, I'm going to stop here.